This is a quick video on section 13.6. Specifically, we're going to look at plotting the gradient. And the gradient, we're going to visualize this as a vector. So this section is also known plotting the gradient, the gradient as a vector field. Okay. And we'll see more about fields, vector fields in the future. This is our first example of a field. So for example, if you have the function f of xy is xy plus y squared, right? We know that the gradient of this function is the vector of first partial derivatives. And so in this case, this would be 2xy, and then the partial with respect to y would be x squared plus 2y. Now, the way you're going to visualize this is that the gradient at any point x comma y, that's what this is right here, the gradient at any point xy. If you pick a specific point at a specific point, say x naught, y naught, okay, and let's say that point x naught, y naught, let's choose that to be 1, 1, okay, you will get 2 comma 1 plus 2, which is 2, 3. The way you interpret this is at the point, the way you interpret the gradient at a point is you go to the point 1, 1 in the xy plane, okay. Here's your point x naught, y naught. And then you plot 2, 3, 1, 2, 1, 2, 3. You plot that as an arrow at this point, x naught, y naught. So this arrow or this vector is your gradient at the point 1, 1. And it is the vector 2, 3. Okay. Now, if you can imagine doing this plotting of the gradient at any point that you pick here, you will see that, and they don't just have to be positive y values, they can be negative y values. And this is just, I mean, these are not the exact arrows. This is the only exact arrow we have. The point that I'm trying to make here is that if you pick a different point and draw a vector, which is plugging in that point into the gradient at that point, you will get a bunch of different vectors at each one of those points. And so the whole sum total, all of the vectors, make a vector, and they make a field of vectors. Okay? In physics, you'll run into electric fields and magnetic fields. So the magnetic field would be a vector field, B1, and this vector doesn't just have to be a vector of numbers, it can be a vector, okay, of functions, B3 of x, y, z. Okay, so here is a 3D object, 3D vector, and each entry, so this is a 3D vector field, of 3 variables. So this is a otherwise known as a vector valued function in 3 variables. And this would be an example of your magnetic field. There's an electric field and it would be the same thing. But just replace this with an E1 and E2 and E3 and make up your favorite functions that have x, y's, and z's in them. We're going to keep our vector fields rather simple at the moment. We're just looking at the gradient. It is a vector valued function in 2 variables. That is our gradient. Okay. So what I want to show at this moment is how to generate this plot really quickly of a vector field, specifically the gradient. Okay. So to do that, we'll go to Mathematica. And it's a pretty, excuse me, a pretty simple matter, pretty straightforward matter, I should say, to let's go ahead and make the function. Let's make the function, and what was it? X squared times y plus y squared. Okay, so there's your function of two variables. Now we know that we can create a contour plot. We can create a contour plot of this function. Okay, it's a function of two variables, and when I plot it, let's go from -3 to 3, and y, let y go from -3 to 3. It is a 2D plot. It's a function of two variables, and here we are seeing all the different contours. Our contour plot of the function of two variables. There's an interesting plotting option that you can add to the contour plot. If you add this in, contour labels, this particular combination will add in to each contour what z level it's at. So this is the z = 5 contour. If you look at this surface and look at all the values that are at a height of z is equal to 5, you will see this would be what your surface would look like. This is at a height of 5, and this is at a height of 5. Okay. All right, so that's the contour plot of the function. It's a 2D plot, so why don't we give it a name? We'll just call this a contour plot of the function f of function. Okay, kind of a long name, doesn't need to be that long, but okay. So let's then add a plot of the gradient. Okay, so if you look at the gradient, let's make the gradient of our function, gradient of f. Remember that we do that by taking the derivative of f of x and y, and then you take the derivative with respect to x and y. And that should make our gradient, which is what we saw before. Here's f sub x, here is f sub y. Okay, so there's your gradient. I like to create a plot of the unit vector that make the gradient a unit vector. So if I bring this code in, unit gradient, I'm just going to take the gradient and divide by its magnitude. Okay, so this now is a unit vector, so there's my unit gradient vector field. Okay, and you can bring in this plot here. If you do the plot of the gradient, let's just call it gradient plot. Okay, I'll show you the difference between the plot of the gradient, and you simply type vector plot. We were trying to plot the gradient as a vector field. And let's say you just plot the gradient of the function f of x, y. And then you want to plot it over the same region that you did for the contour plot. Okay. So this plot should be a plot in 2D. The gradient has only 2 entries to this vector field. So when you plot this, you should just see arrows that are in the xy plane. Okay. Now notice that some of these vectors, as you get near the origin here, you can barely see them, and that's because that the gradient is changing length from point to point. So take a look here. If you look at your gradient of your vector field, let's say at the point 0.5, 0.5, and you compare that to the gradient of the function at, say, this point over here at, say, 3,3. And look at those two vectors. You can see that if you look at the length of this vector, it's very small, and this vector has significantly more length, right? So if you're just plotting the gradient of the vector field, the gradient will change from point to point, and the vector will be different lengths. So it's my preference to plot the unit gradient vector field. So that's when I made the unit gradient vector field. And now you can see that all the vectors are the same length. Okay. Now what we want to do at this point is we want to put this gradient plot on top of the contour plot to see what the relationship is. You could add a couple extra plot options here. You could say frame label goes to X and Y. Okay, so now you can see that I can see what the X direction is and what the Y direction is. I like to make the vectors maybe not quite so large. So if you bring in this option, these are just things that you kind of learn along the way. Vector style. Now I can see that the vectors aren't quite so thick, so I just made the arrows a little bit smaller. Okay. So what we want to do, and let's see, can I say, let me see if this works. This is a guess. What if I want the vectors to be red? Would this work? Yeah. Let's resume. We're trying to plot the contour plot on top of this gradient. And we see that now the gradient vectors are in red. And if we do a show command and you say contour plot of function and gradient plot, we can see now that, let me switch these back to black. I was thinking that red may be more visible with the black arrows. And I think you can see here, hopefully, the relationship that anywhere this gradient vector crosses a contour, there's a perpendicular angle at that point. So if you pick contours, if you plot more contours, contours goes to say 20, plot more contours, everywhere the vector crosses a contour you can see that it'll be perpendicular, right? So that is the relationship of the gradient to the contour plot of a function of two variables, and how to plot the gradient as a vector field. One other option you may find kind of helpful at this point is there's something interesting here. If you say plot legends, and just say automatic, you can see here that there's a plot created, and this will show you what the colors mean in this context. So here the blue color is a large negative number and the light tan is a large positive number. So these blue and gold colors are kind of arbitrary, but if you were to change this to color function and change it to temperature map, you'll see that the colors may actually mean something now. Okay, so here's a plot of our function and the contours, and here is the plot legend. And now we can see that these numbers actually mean something. Usually red indicates hot or larger numbers, so this is the hotter part of the plate, the temperature plate, and blue is usually colder, so this would be the cold temperature. So this, if this were a temperature function, okay, all the points that are at the same temperature are shown, right? So here are all the points that are at a temperature of 5.7 along the plate. Here are all the points that are at negative 5.7. So there's some points over here that are at negative 5.7. There's some points over here that are at negative 5.7. So those are just some of the features that are available to you when you're plotting these contours and showing the gradient.